All right, so what we were just looking at is the difference between our maximum approximation and our minimum approximation. And what we recognized is that these green boxes, this is in my maximum approximation. It's the only value in my maximum approximation that's not in my minimum. And this here is in my minimum approximation, and it's the only value in my minimum approximation that doesn't appear in my maximum. So the possible error is the difference between those. So it's a difference of, the error is a difference of 8 minus 2, because every other value is the same. And so the only difference is that my maximum has an 8, where my minimum has a 2. So the error now is 6. Notice that the error between the error here is 6, whereas the error in the last approximation, going backwards, the error in the last approximation was 12. And that was the same data set, only looking at 2-second intervals. So when we had an error of 12 when we were only going up every 2 seconds, whereas when we were going up every 1 second, we had an error of 6. And this is demonstrating that the shorter or the more time intervals that we have, the more data points, the greater our approximation is going to be. All right, so let's continue on a little bit conceptually. The idea here, here's velocity and time graphs, and on the upper part up here, this is our minimum approximation. Notice that in each time interval, like from 0 to 1, I could have chosen the max volume or the minimum volume. And since I'm looking at my minimum representation, I chose the minimum. And I let that area under the curve approximate the minimum distance that we could have gone in that 0 to 1 second interval. Whereas below, I have a maximum approximation. So in that same 0 to 1 interval, instead of choosing the left point, I chose the right point, the bigger point, and from there constructed my distance approximation. Because remember, the area under the curve, this area is our distance. So here's a bunch of data points for those curves that we were just looking at. And so going back, this line and this line, the same lines, and I was going up by 1 second intervals. Now I have the same data, only I'm going up by 0.5 seconds. That's my increments. And what we want to look at now is the idea of difference between estimates. So in other words, what's my error between my max estimate and my minimum? So if we look at this chart down here, the green areas are the minimum estimates. They're choosing the left side point, the smaller value. They're choosing the smaller value of the velocity in those given increments. And so the areas that I'm drawing are the estimation for the minimum distance traveled. The shaded region, that blue region, the already shaded in blue, or already shaded, which I'm now putting in blue, the blue plus the green, that's our maximum estimate. So, this here is the maximum. So in each 0.5 second interval, that shaded region, so let's see that a little bit better. That shaded region is the difference between the estimates. And if we add up all of those difference between the estimates, that's what this is right here. It's adding up all of these boxes, stacking them, adding up all the blue boxes and stacking them on top of each other. So if we look at each of these blue boxes and then consider sort of like smushing them to create one big box, the height of that box would be 480 minus 180, and it has a width of 0.5. So this width here is 0.5. And so the difference between our estimates would just be the area of this blue region, which is 300 times a half, which is 150. Well, the other way that we could have found that that difference, what we were looking at before, is that the only difference in our max and min estimations are going to be at our left point when I choose 180 for that first 0.5 interval. So in my minimum, I'm going to have 180 times 0.5, and that's going to be the only value that exists in my minimum estimation that doesn't exist in my maximum. And in my maximum, the only value in my maximum that won't occur in my minimum is going 480 for this 0.5 second interval. So my maximum, I'm going to have 480 times 0.5. And so the difference, doing the same thing is going to be the difference between these two points, which don't exist in the, which exist in the max or exist in the min, but not in both. And this value here that we're constructing, it's the same thing as this. It looks a little bit different, but if we calculate it out, factor out a 0.5, is exactly 150. So this is just two different ways for us to sort of intuitively understand our difference between a maximum estimate and a minimum estimate. Now again, what we're doing is we're approximating area under the curve. And this is going to be a big topic for us over the next, bunch of weeks. And for these velocity time graphs, we've said a couple times, the area under the curve equals our displacement. And a key thing is for increased accuracy, the way that we can do this, get a very accurate representation for displacement. If you can notice between these two curves, my curve up top, the blue areas are over approximations. They're not accurately depicting the area. Whereas in my curve here, I don't have those great errors in my approximation. So for increased accuracy, it's very clear comparing these two graphs, graph 1 and graph 2, that the difference is that graph 2 has more data points. So we're increasing data points, and we're increasing data points by reducing the delta x. So we're reducing delta x. We're letting that distance between each x point, get smaller and smaller and smaller. All right, so the last thing we're doing is one more word problem, and we've got a cross-country skier. It's fitting for our school, and this is an interesting problem because the velocities aren't increasing monotonically. So velocities going up and down and up and down. So it says, given the information in the table, what's the minimum possible distance during the first 3 minutes? So we look at the first 3 minutes. We've got 150 and 360. We're looking for a minimum distance traveled. So we'd say 150 times 3 minutes, 450 meters. What about the minimum distance traveled in the second 3-minute interval? So in the second 3-minute interval, between 3 to 6 seconds, we could choose either going 360 meters per minute or 0 meters per minute. Since we're looking for the minimum distance, let's choose the smaller velocity, 0, for 3 minutes. So we'd go 0 meters in our minimum distance approximation. Okay, So what about continuing this? Uh, what if we wanted to go between 6 and 9 seconds? And we want a minimum distance approximation. Well, our minimum distance would be using a velocity, the smaller velocity, in this case, 0. So we'd say we went 0 for 3 seconds, which is, or for 3 minutes, 0 meters. And then and this is between 6 to 9. And then we'd continue this from 9 to 12. So from 9 to 12, choose the smaller velocity, 320 times 3, which equals 960 meters. And again, this is from 9 to 12. And then from 12 to 15, we'd be going, choosing the smallest velocity, 180 times 3. So our minimum distance approximation would be that we went 450 in the first 3 minutes, 0 in the next 3, 0 in the next 3, 960 in the next 3, 540 in the last 3, and so we'd add each of those up. And when we add each of these up, 450 plus 0 plus 0 plus 960 plus 540, that will get us to our minimum approximation. And our minimum approximation, adding those all up, is 1950 meters. Well, what about a maximum possible distance? So for our maximum distance, we're going to do the same thing, only for each interval, we're going to choose, the biggest velocity. So for our maximum, in the first 3-minute interval, we would choose 360 times 3. And then in between 3 to 6 seconds, let's choose 360 again. And from 6 to 9 seconds, we are going, I think that's 400. So plus 400 times 3. And between 9 and 12, the bigger value is 400 again. So 400 times 3. And between 12 and 15, the biggest is 320 times 3. So we go ahead, we add all these up, and we get our maximum approximation. Our maximum approximation being 5,520 meters. So our maximum approximation is significantly bigger than our minimum approximation, and that's mostly because of those a couple occasions here where we had us going 0 meters per second for 3 seconds and then 3 seconds. So for 6 total, or 3 minutes and 3 minutes. So for 6 minutes in my minimum, I was going 0, where in my maximum, I was going pretty fast. This hopefully illustrates the idea behind creating maximum approximations and minimum approximations using data tables and using graphs. The big thing here, the big idea from this, going back a slide, is that we're finding area underneath a curve, and in order for our area underneath the curve, which we're approximating with rectangles, for that area to be most accurate, we need to let this delta x, this change in x, get smaller and smaller and smaller. So we want to let delta x approach 0. And that's really the key idea here. We'll do a lot of work kind of creating much more structure around this idea of area underneath the curve. Again, this is the idea of integration, and it's the next big topic in calculus.